Now I'd like to continue with the pretty long talk. I have 1 hour talking about the EMC simulation of an electrical vehicle powertrain. So I hope it will be interesting for you because I'm actually convinced that we have some very nice examples to show here. So if we talk about electric cars being it a hybrid or being a full electric vehicle, you typically have the same type of system for the drivetrain. So you have a battery providing the current, then some cables which route the DC current to the inverter. The inverter converts the DC current to the AC current which is needed by the motor. So you can see here the AC current flowing over a bunch of other cables to the motor, and of course the inverter is controlled using some controls. What we will not talk much about today are the controls, because that's a pretty different regime, I would say, but we will take a look at the EMC performance of all these components here and assemble them after on to a full system. Why is this so important? Of course, electric vehicles, I think, are the future of mobility. There's a lot of development going on in terms of electric vehicles, and I pick up one important value which tells us why we need so much in EMC is the AC current. So the current flowing from the inverter to the vehicles, even in the small hybrid cars, it's as high as 300 amps, and going to high-end cars, maybe it's somewhere between 500 to 1000 ampere. So it's a very high current, which of course will create very high fields. And this is a challenge to the designers and a challenge to the EMC performance of such a vehicle. And at this point, you already arrive at, let's say, at the conclusion that I gave in the first talk is, if you do not include EMC at the early stage design of such a powertrain, you will probably have a lot of problems. So this current values are so high that you need to already think not only during the integration of these components into the full vehicle, you have to think not only about, let's say, crash safety of these components, like the crash safety of the battery, you have to think how you will shield or how you will control the electromagnetic fields created by this very high current flow. It's integral part of the vehicle design at this point. Of course, for combustion engines, it was never like this. There were not such a high current. But at this current regime, you have to make sure that you include EMC very early. And there are a lot of challenges. I mean, of course, the whole vehicle EMC, certification, product safety, all these questions that you had also with the internal combustion engine, but maybe not at such a high level. But there are new challenges, especially for the low frequency magnetic field for the human safety. With such high currents, the magnetic fields, the low frequency magnetic fields, or let's say, the frequency is typically around a few kilohertz. The fields created by these high currents, they are well in this regulation standards, for example, by ICNIRP. So like you have SAR for mobile phones, you have also limit to exposures for low frequency magnetic fields. And with this currents about 500 hertz, you will come to a region where you have to make sure that you comply with the standards. They are not only the ICNIRP, also, for example, on the Chinese market, there are new regulations which even make sure that the magnetic field is below a certain threshold for very different driving scenarios of the electric car. Of course, the magnetic field depends on the power that currently the motor is providing, and all these things need to be tested. And this is my topic for today. All the stuff that I'm showing you has been calculated in the same approach that we showed you in the last two presentations, basically using a 3D full wave simulation and coupling it to the circuit. So you have seen how we do it. Now let's apply it to more complex examples. And the first thing I would like to talk about is the DC current, or let's say the cables providing the DC current or the cables providing AC currents, and how we can simulate cables and get estimation of the low frequency magnetic fields. So I start in this, I have a few examples, but I start first with a very single wire. So we have a single wire which is connected to the boundaries here, and we would like to see the magnetic field which is created by the wire when there is a 500 ampere. So that's somewhere in the middle of the table that I showed you before, and I use a 500 ampere current flat over all the frequency band. We look at the frequency from basically 1 hertz to 50 kilohertz, so really low frequency. And if we look at the field the magnetic field which is created by the wire. It's pretty obvious. It's circular around the wire, and of course there is no frequency dependence. If we have 500 ampere current, then at all frequencies, then also the magnetic field will have the same value, which is here at 10 centimeter distance, 790 amps per meter, and the ICNIP standard is typically somewhere, keep in mind, something like a value of 200. So already at the 10 centimeter distance to a wire like this carrying 500 amps of current, you are far above the ICNIP limit, and you have to limit the fields. So simple wire, of course. Now we would like to add shielding. We have seen that the field is high enough, too high, we have to shield it. So we add a conductive wall here. It's at 3 meter distance, has a 1 centimeter of thickness, and has a, let's say, not too high conductivity. It's the conductivity of steel, but I keep right now the permeability at 1. And we measured the fields by using such probes. It's again 10 centimeter distance like we had before. Typically we will look at this probe, which is called behind here, simple. How does the field behind the wall look like? And if we do this, so first I did it for the conductive wall, and what you get is the blue line, which is the, let's say, the field when the wall is purely conductive. So you can see, of course, at the 1 hertz and so on, there is no shielding, and then once induced currents are happening into the wall, a shielding effect is created and it drops off very nicely. Then I have not only taken a conductive wall, I have taken a permeable wall without any conductivity, and you can see that the shielding effect of a permeable wall is pretty different. It's not frequency dependent like in a conductive wall. It simply drops the whole field by a certain amount, which depends, of course, on the permeability, and we get a reduced field here, which is flat over all the frequencies. And then last but not least, I choose something like a magnetic steel, where we have a permeability and a conductivity, and we see that the effect of the permeable shielding, it first goes down, and then the effect of the conductive shielding going downwards here. So we have 2 types of shielding basically at the low frequency range, not at the low, it's also valid actually for high frequencies. We have a so-called, what I call the eddy current shielding. We have the induction of currents inside the conductive material because we have a time-varying field. This induced a current inside the material, and the current direction, the induced current direction, is opposite to the source current, which creates also a magnetic field which is opposite to the source current, and then we have an overall reduction of the net field. So this is the eddy current or inductive shielding, while the permeable shielding works pretty different. As we have seen, it's no longer frequency dependent. So what is happening is that the permeable shield is changing the distribution of the magnetic field. It's basically pushing the magnetic field in front of the wall and not allowing it basically to happen behind the wall. What is not happening, and I read this several times on the internet, the permeable material is not absorbing the field, not in the kilohertz region. So there are no losses, there is no heat transfer, the field is deformed. Let's say the distribution of the field changes, but the field is not absorbed. This is only happening typically in the megahertz range, like when you have maybe a ferrite clamps over your cable and you absorb a 300 megahertz, that's where you have absorption. At the low frequencies there is no absorption. The field is basically deformed. That's what's happening. And we can see also, if we look at the magnetic field, we can see these different effects. So this is for a conductive wall. You can see that the magnetic field is tangential to this conductive wall. For a permeable wall, so purely permeable, the field is completely different. And of course, if you have a mixture, the field distribution will look like a superposition of this both. So it's important to understand these things, that you have 2 kinds of shielding, and it's important also to understand really there is no absorption by the permeable material. It's just let's say, reforming of the magnetic field. So what we had up to now was an infinite wall. A wall, it was not infinite, the wall was connected to conductors at its side. So the induced current could take a path over these conductors where the wall was connected. What happens now if I make this shielding plane smaller? It's no longer connected to this, so that was electric boundaries, it was conductive. If I move the shield away from it, so there is no way for the current to close over the boundaries, we can see that actually this affects a lot of our shielding effectiveness. So this blue curve, which goes nicely downwards, which gives us very, very nice shielding effectiveness. This was just for the wall which was connected to the walls, to the boundaries. If we make a distance between them so that the currents, the induced currents will close inside the wall, then our shielding is degraded. And you can see this, what's happening is actually, the induced currents, they are also flowing in a loop. The loop has to close, and the loop will close over the edges of the wall, and the current can basically get to the other side of the wall. And then you are losing the shielding effectiveness that was working so well when the wall itself was connected to the boundary. So you can see there is some effect. So this is as long as the current, let's say, not getting around there, but then your shielding is basically constant and it does not improve with frequency. So that's a very important effect, that your shielding property is not only depending on the material, but also how the currents flow in this material and how this material is connected to other parts. So for example, if you think like integrating some shielding parts into a vehicle, you have to make sure that in your simulation you consider how the shielding parts will be connected to the rest of the chassis, because this will change the current distribution and will change your shielding effects. So this was like said, let's say for a wall. If we do it like for a wire, now we have a inner conductor and a shield around the wire. I do the same thing. So there's the same type of materials. We have a conductive material, a permeable, and a material which has both. And a surprising thing is that you can see if we put a purely permeable shield around the cable wire, we see no shielding effect at all. And this is the reason is that the magnetic field, if the surface of the shield is tangential to the field distribution of the magnetic field, basically the magnetic field can penetrate this conductor, this permeable material. You can see it also here. If you look here at this position, actually the magnetic field of the wire would be tangential to the surface, and then you see no shielding effect and the magnetic field can penetrate. I think it's a pretty strange finding, but that's really how the magnetic field will behave. So basically it's pointless to use permeable material for shielding cables. So that's why typically also the cable shields are done from conductive materials, and we get kind of response which is similar to what we've seen in the wall, but of course depending on the thickness of the wire, shielding will start earlier with frequency or will come later, but the behavior itself is the same. However, if we now, in this example I showed you before, the cable shield was actually again connected to the boundary so that the current loop could close over the boundary. If I now make the shield, let's call it floating, it's no longer connected to everything, all of your shielding effectiveness is completely gone. So there is no shielding at all if this shield is floating. And the reason is, again, if we think of the loops of induced currents. So when we had the shield connected to the boundary, then inside the shield the current was just flowing in one direction, and that was the direction opposite to the source current, and we get a shielding effect. If the shield itself is floating, the induced current still has to close in some way, and what will happen is that will close along the path of the current and will create a loop inside the shield itself. And this loop, of course, has now, it's not opposite to the source loop, and this is also why we not see any shielding effect of this. And we see this effect continuing when we then talk about on the next slides on 2 or 3 wires, that this is basically what you typically call in the industry the bonding of the cables, which makes sure that the current in the shield is not flowing like that the current loop is not closed in one of the shields, but has to flow in between 2 sheets. Okay, that's a better example now. So we have the 2 inner wires now, because now we no longer close the current loop over some boundaries, but we have a current loop. Let's say it could be like the DC current, the DC cables connecting the battery to the motor, and here with this port we can drive the 500 ampere. And then we have this blue sections which connect the shields, and I put in a variable resistor. Basically that's your bonding itself. So this could be this like a part of your enclosure, and we put a bonding here, and we can vary the resistor value to see how does it affect the shielding. And we can see, okay, at 0 milliohm, so basically ideal connection here, we get a very nice shielding. But already at 5 milliohm, the blur curve, our shielding has been reduced by let's say 10 to 15 dB. And at 50 milliohm, when we put this resistor here of 50 milliohm, basically the bonding, your shielding is almost completely gone. It's basically completely gone. So the effect we see here is because the wires are so close to each other, and this is some proximity effect. That's why this curve goes down here. But it means that if you have a good shield, you also need a very good bonding. Otherwise, your shield will no longer work. And the explanation is again the same like we had in the single wire case. If we have a low impedance bonding, then the current can flow between these two shields, and it will create a loop looking like the green one. And this loop is completely opposite to the source loop, which is the yellow one, and this creating a shielding effect. If the bonding between the shields is too high, then you see already here that the current is flowing inside each shield separated from each other and is not creating any shielding effect. And this value of the 50 milliohm actually depends on the length of your cable. So the longer the cable, the worse you can have basically your bonding. It's simply, the current will always choose the path of the lowest impedance, and it depends if this is the lowest impedance, the red loop or the green loop. And that's exactly what you can see is such a test. So I use the same bonding impedance of 10 milliohm for all tests, and I make these cables longer or shorter. And you can see that I mean, if everything is shorted, which is the gray curve, the length of the cable doesn't have any effect. But if I add the 10 milliohm, then for the long cables, let's say the loss in shielding introduced by this bonding resistor is not as significant for long cables as it is for short cables. So you can really check this with the simulation itself. Excuse me for a second. I just have to take a watch to see how I'm in time. Okay. So that's, I think, a very well explanation for a typically well-known fact that you have to have a good bonding, and you can see how you can use the simulation also not only to estimate values, but really to get an understanding of the effects that are happening there. And then I have run a few let's say parameter sweeps of now having 3 wires, arranging them in a triangular symmetric fashion, and first testing, okay, what's the effect of the conductivity? Of course, with increased conductivity, you get a better shielding. It's looking not that bad, but you can also notice that, of course, it's a very high value. It's like a factor of 40 or so that we have increased the conductivity going from steel to copper, and that's exactly what we see in this plots, that the shielding has increased with conductivity. We can of course also increase the shielding with thickness, but it's obviously much more difficult to get a factor of 40 in the thickness like we get it before in the conductivity. So increasing the conductivity is a good way, but of course it's limited at some point. You will not find a material which is better conductive. Then you can also increase the thickness, but don't expect too much from increasing the thickness. One important thing is, of course, that it's not only the shields itself and the current, it's also the arrangement of your cables. And what I did is I swept the distance between these cables going from 4 centimeter to 1.6 centimeter. Basically, that was the closest you could get these wires. And if you put them close, you get a reduced magnetic field, obviously, because the area of your source loop has been reduced. And it's a nice thing to see. It's basically for free. You didn't need to increase any of your shields. You didn't need to increase any of the thickness on any material. It's just reduced simply because you have a better arrangement of your wires. And even recently done a simulation, if you would twist the wires, you could also gain a little bit. Of course, it's limited to, let's say, typically like maybe a factor of 2 or 3 that you can gain out of it. But you will not gain like maybe 20 dB or something like that. For this, you will need still a shielding of your wires. So summarizing the part about the cables, I think, you can use the simulation to understand, to gain insight of what's actually happening, to see this different shielding effects of the eddy current shielding and the permeable shielding, and also to see, I mean, this is something that you can read in a book, but once you come to finite sizes, like the finite shield size, when I have moved the shield away from the distance, that's something that you will typically not that much find in a book, because simply the expressions or the analytic solutions to these models will become complex. For an infinite half plane, you can find it, you would typically do it like in a book which you read during studies. But for a finite plane, things become much more complicated, and that's exactly where your simulation can help you. Even you see, the models I have simulated are not that complex. It's basically just cables and the shield, but it gave me a lot of insight on what's actually happening and why do I need the low impedance bonding, and if moving the conductors is better or increasing the thickness of the shield. I can test all of these things using parameter studies. And these models, again, as you had the question about the simulation time, these models, when you have a really fine resolution to see also the currents inside the shields, it takes maybe 2 to 3 hours. If you do just a rough estimation, which gives you already a pretty good answer on comparing these results, you can do it then in 10 or 15 minutes on a laptop when you are not really looking into the finest details. How does the field look inside the conductor or things like this? If you just want to calculate the magnetic field, it can be done in a few minutes. So that's my part about the currents and the cables. I would like to continue talking about the inverter itself. I think the inverter is really like, when the controls at the brain, the inverter is the heart of your system, because it pumps the energy from the battery to the motor. And it does it a lot by switching, and the switching is of course a problem for EMC. And this is the kind of inverter that I would like to use in my simulation. So it's, I think, a very typical IGBT package. So the CAD model we have loaded from the 3D Experience platform, and then of course we need to define the electromagnetic setup for inside CSD Studio. So first thing is of course to put ports, like Waldemar was showing. The ports are always you bridge between the 3D and the circuit simulation. Of course, we will model the semiconductors, the IGBTs and the diodes on the circuit, and therefore we put the ports. So you can see here, this is a diode port between collector and emitter, and here's the gate which will control the switching of the IGBT. Actually, if we go back here, there's a pretty complex model, because if you have like, 3-phase H-bridge setup, you have 3 high-side transistor and 3 low-side transistor. But in order to split the current evenly here, we have 3 high-side transistor in every channel. So that's a lot. We have 3 high-side transistor here, here, and here, which gives us 9 high-side transistors and 9 low-side transistors. And the aim here was, of course, obviously to split the current between them in order not to have any thermal problems. So this is the setup we have. That's why it says ×3. So we have 3 transistors in every phase. I mean, 3 transistors on the high side, 3 on the low side for every phase. And typically this will be driven by a PWM signal, which will be created by the controls. But as I said, we will not include the controls, simply because we are more looking now into the EMC things. We have such a macro inside CSD Studio which can create arbitrarily PWM signals, and they will be applied to the transistors we would like to simulate. And here this section is currently at this point in time a very simple model of the motor. I will show you later on how we can also increase the accuracy of such motor models. So just as putting this both next to each other on a schematic and on the 3D model, we have this, I think I have pictures here. So this is the current going in, the positive clamp, the negative clamp. Each of the 3 phases has its own clamp. Of course, sometimes you also have just one clamp providing all 3 cases. This is where the connections are in the IGBT module, and then we have the 3 outputs of the output current, typically called U, V, and W, which feed the motor afterwards. And the switching is happening here to create this PWM signals out of the DC coming from the top. The first question now, as I always said, it's we should start simple, is we can also do simple on a circuit. So of course, most of the semiconductor vendors, they will provide you with SPICE models of the devices, but some of the semiconductor vendors have a very, very complex SPICE models, and simulating them can be also time consuming. So at this point, when we talk about very long time domain simulations, coupled to the 3D model, time domain circuit simulations, coupled to the 3D model, sometimes they will also need a considerable time. So it's no longer that kind of 1 second simulation with a resistor and with a capacitor. When we couple the 3D model to the circuit, of course, we also increase the complexity of the circuit model itself. And in the first step, it's not a bad idea to use also simple, let's say, semiconductor models. And what we did here, we took a switch, ideal switch instead of the capacitor. And if we compare this, the motor currents, the DC currents look pretty much the same. Of course, not everything is correct, which that's a simple model, because, for example, the current flowing through the gates is more accurate in the IGBT model than in the voltage control switch, but we are 4 times faster. So this is also, again, when building up these models, start simple, which would mean at this point also not only use maybe, let's say, a stripped down geometry, a simple geometry, but also use simple circuit models to make sure that the simulation is running fast and you set up the correct response. I mean, when doing EMC simulation of such a system, before I look at the listen, before I look at the emission of the system, what I need to make sure is that the system is doing what it's intended to, and my cross-check is of course looking at the motor currents. The system should create a 3-phase sinusoidal current driving the motor, and as long as my simulation that I did is not providing this, I don't need to look at the EMC results. I have to first make sure that actually I'm simulating the system that I want to look into it. So that's kind of sanity checks you need to do during the build-up of such a model. And then we can, of course, use our nice combined results feature that we have introduced to you and look, for example, at the different phases here. So this is the phase where the DC current comes in over the W phase, flows through the motor and goes out over the V phase, and that's exactly what you see here. So this is the current back, so this is the V phase. The current flowing from the DC plus is going here, then over the bond wires down here. The motor itself is currently modeled in a very simple way. We don't have a 3D representation of the model, and then the current flows back over here and the loop is closed back here. So that's a starting point, and it allows you to see how the currents behave and how they look like inside this IGBT module, as we can see here for the 3 different phases. It's a nice visualization. Also, seeing things is sometimes believing in things. So the inverter itself, we build up such a model, but of course we want to include this inverter model into a more complex model, and we will now assemble step by step. I mean, the first thing of the inverter is, of course, we know it switches a lot of current, so the current should go to the motor, but on the other hand, it switches the DC current with a lot of switching, and we could see the DC current here. So you can see this is the DC current. So all this noise, all the switching noise will probably flow back to the battery. And this, of course, something that you don't want to have and you need to filter. So the next step, what I would like to show to you is like a filter for the DC current flowing from the basically placed between the inverter and the battery. And it's a pretty simple model that we have created here. You have to see, we are creating these models at CSD. Or at Dassault System. Of course, we are not car builders. We are not building these things in reality, but we have models which typically represent the reality pretty well. So what we have is this 3-phase filter coming in. We have 3 capacitors between the phases, so CX capacitors and 3 CY capacitors, and we have a ferrite, basically a common mode choke, which is placed around these 2 traces, which should which should reduce the common mode emission here. And such a filter simulation is, I think, is very straightforward. It's again, I would consider this to take maybe less than maybe 20-30 minutes on a laptop, and we can take a look at the response. So this is like the attenuation of the voltage. You could of course also calculate the attenuation of the current. On the one side a voltage is injected, I think one volt is injected, and then we see how the filter is attenuating the common mode, the 1 volt common mode on the output. So this is something, a very typical and straightforward simulation that has been done for many years. But what I would like to show to you is now how we deal with the ferrite clamp, because it's a pretty new feature that we actually have only since last year. Of course, the ferrite materials, we have seen ferrites as used as a shielding, for shielding in the previous example. Now we use the ferrite as a kind of clamp to filter the common mode noise. And a ferrite itself is of course dispersive. So the let's say the mu value is depending on frequency. That's what we mean by dispersive. So in this example here, you see at around 10 megahertz, we have, so this is a pretty fast ferrite actually, a one which is a pretty high, let's say a frequency over here when the permeability is basically halved between a mu static and a mu infinite. That's happening at 10 megahertz. It's pretty high frequency, but typically what a ferrite will have that this tipping point is somewhere between 10 megahertz maybe to 1 megahertz or to 500 kilohertz. So this curve is moving depending on the material, on the ferrite material itself, and you will have some losses. So this is typically a curve which we can easily incorporate into our 3D simulation. So including the dispersion of a material is not a big issue inside Microwave Studio. What's far more complex is to include the non-linearity. That means the saturation effect inside the ferrite. Because when you have something non-linear, like a saturation effect, you have to loop a few times the simulation. What you typically do in a so-called nonlinear loop is you calculate it with the source current that we have given, you calculate the field distribution, then you check what are the field values at the positions of the ferrite, adjust the ferrite values according to the nonlinear curve. So the nonlinear curve gives you the effect that at higher field strengths the permeability is lower. And you loop this a few times until you get a distribution which no longer changes. And then you know that parts of you, because at certain currents only parts of your ferrite will be saturated. It's not a binary thing whether the ferrite is saturated or not. Some sections of the ferrite might be saturated while some other sections will not be saturated. So you really get a distribution of the permeability inside this cylinder. And now it's a pretty new thing. What we have is we can couple these two together, because up to now this were really separate simulations. We could not include both effects at the same time. And the new idea is to really use two solvers. You have to do it. You calculate first with the so-called magnetostatic solver. I mean, why static? Because typically the BH curves, the saturation curves, are always measured at static frequencies. I've seen a few papers measuring saturation at higher frequencies, but it's not common, and typically it's difficult to get this information. So that's why what we do is we first run a magnetostatic nonlinear simulation to include the effects of the saturation itself. And you can see here how this core is basically partially saturated. So the current flowing through these two bus bars here is creating, of course, the closer to the bus bars you are, the more saturated the material you get. So our permeability is reduced in these regions, while at top it's not. So this distribution we now take after the nonlinear simulation has been finished, and we use this distribution basically as the mu static interdispersive model. So what is happening is that this curve, this like inverse S curve, will have different starting values, will have different shapes, but we are just changing the mu static, basically this value, And this will have these different shapes in all the regions. So basically inside the mesh, when you simulate, all the different regions inside the mesh will now see a really like spatial dependent dispersive material. And I think this is a very nice step forward for modeling ferrite-based filters and ferrite-based chokes. And it's a new thing that we now have in the, I mean, it's already there in the release 2020, and you can even download a tutorial on the Dassault System webpage how to set up this type of simulations. And then just as a cross-check, we can see here how the common mode current is attenuating depending on really the DC current put there. So you can see that there is a frequency shift depending on the DC current flowing through the bus bars which are enclosed by the ferrite material. I think it's very, very nice workflow that we did not have like 2 years ago. And I think it's a really nice extension because as we talk about the drivetrain, the currents flowing there will be high and probably your ferrite material will saturate. And now that's something we can include. So this is the filter part that I liked to show you. Now let's move on to the motor itself. I mentioned already in the beginning at the inverter simulation parts, we have used a very simple motor, basically 3 inductors on the schematic, but that's pretty simple. And what we want to build is, of course, a more advanced model of the electric motor, but not a model which is used for force calculations. I mean, the guys who are designing these motors, they have a very strong interest in the force, of course, because that's the creation of the torque of the motor and in the losses. And these are the key points for a machine designer, while for an EMC engineer, the key points are different. We are not that much interested maybe if the losses, because we don't want to optimize the design. But what we want to see is, we don't look at the torque. But what we need to include in our simulation model is what are the parasitic coupling pairs from the motor. And in such a typical motor as we see here, we have basically 2 possible paths. One is the coupling of the stator winding to the rotor shaft, to the inner part here, and the other is coupling of the stator winding to the enclosure. So both there is kind of, let's say, parasitic capacitance, where the current will flow at higher frequencies because it's a capacitance. And this coupling is of course important for us, because this coupling will determine how the common mode flows in the complete system, from the motor maybe back to the inverter over some chassis parts. But what we don't want to do, I mean, this is the 3D part. We need to have a model which gives us the correct parasitic capacitance, but we don't want to model the full motor simply because it's too complex. I mean, in the past half year, we had 2 or 3 projects where we really modeled the motor as a full wave 3D with everything. Maybe in the future we will move towards this, but right now we were looking for a simpler model. And therefore we create the kind of hybrid model. So the 3D model needs to represent the capacitive coupling, while on the circuit I need to have the proper inductance, because the inductance of course will I need the proper inductance to calculate the right current flow on the schematic. So let's say the functional current needs the right inductance, and the EMC coupling, parasitic coupling, needs the proper capacitance. So this is why we spent some time on creating such a simplified motor, and my colleague did a few tests, basically, you know. It started with a full-blown motor, but then thought, okay, how can I simplify it? And he did a few tests on changing the wiring topology, changing the number of slots, changing this insulation thickness, and really get an idea of which components of the motor have the highest effect on the EMC performance of the motor. I think it was a very nice study. I'm not going into details here. He created a lot of curves, and he can tell you exactly which of these thicknesses has a higher influence on the parasitic coupling and that kind of things. But the main point is here we have created a EMC, basically a motor model for EMC simulations, and that's helpful because it's simpler than just a full motor model as used by designers. So we had this inverter, we had the filter, we had the motor, you have seen all the components. Now we would like to assemble these things into such a powertrain. So this is a powertrain of the motor. So it includes, you can see here the cooling inlets. The motor is placed here inside this box. There is the inverter, and here's some cabling which is not shown, but here's the cables going from the inverter to the motor and so on. And of course a real CAD model will be pretty complicated. So there will be a lot of details there, and we have such a CAD model also again on the 3D Experience platform. And before going and simulating this with all the details, with all screws, with all holes and so on, we take the effort and we did simplifications inside CATIA. It's a very powerful tool in terms of CAD modeling. So you can see, for example, all these details of the screws, all these details of these plates and so on. They are not that much important for our EMC. Everything which is much smaller than the wavelengths can be neglected. What's important for us are the connections between the conductive parts. And this is how we have simplified also like the cogwheels here, because this kind of teeth, they will not change much on our simulation. And here's the simplified model. So it of course took a few steps to simplify such a whole powertrain model. And this is where we arrived at. So we have the inverter here, we have the shaft simplified again, we have the motor with the packing, and some of the other mechanical components there. The DC cable harness arriving from the bottom, and the AC cables going up here and feeding the motor. And this is now a model that we have simulated throughout and wanted to look at what are the possible common mode paths. And they are basically three that we have identified by looking at it. Of course, it's the drive shaft itself. So here's a port will measure the common mode on the drive shaft. Here are some brackets, and here are some mounting brackets. So typically there's a bracket with some rubber inside where the powertrain can be mounted like or connected to the chassis of the car. And of course these brackets will have some kind of capacitive coupling, and it's of course very interesting to understand at which frequency do I expect a current flowing through such a bracket, at which frequency the capacitance of the bracket will become conductive. And in the first step, what we did is that kind of simulation that you have seen before, where we just excite first one phase. We don't do the whole thing, we will do later, but we don't do the full time domain simulation with all the switching. What we look at, we pick out one phase. So we say here's a source of noise, and what I then do instead of switching these components, I basically short this transistor and short this transistor to create a path basically of one current phase. And we look at this. Why we do this? Because there's a frequency domain simulation, AC simulation inside on the schematic, and it's simply faster than simulating this long switching times. So this is our first step. We will not stop here, but it's a first step which gives us the simulation results a little bit faster. And now we can take a look. So this is the current flowing through the battery, so basically the conducted emission, and here are the currents flowing through the brackets and through the drive shaft. And it's very interesting. So I mean, the orange is the drive shaft, the light blue is the bracket 1, and the dark blue is the bracket 2. So basically this position, drive shaft, bracket 1, bracket 2, and we can see that there are clearly some resonances around 10, around 20, and somewhere around 35 or 38 megahertz, where the current through the common mode current through these brackets becomes significantly high. And now we can go back to our visualization and take a look, how does the current distribution look for this? So if this is the DC current, this is actually what you want to have, and if there would be no high frequency currents, you would have no problems, but probably you will also have no job because the current would stay as DC. But as an EMC engineer, you are looking at how the current behaves away from the frequencies for which the system was designed. And now we go to 380. So I think this is down here, where the drive shaft, where we see a current through the drive shaft, and you can see it also clearly from these pictures. Now if we go up to the frequencies, 9.7 megahertz, is this one. You see both are current through the drive shaft and through this bracket. And then at higher frequencies, 38 megahertz, which is this peak here, the current flows through bracket, through shaft, and also through the other bracket and all this connection, so this high frequency currents. And I think it's pretty interesting and pretty important to look at these things, because this kind of resonances, they are not happening because of the inverter and the motor. They are happening because of inverter, motor, and the powertrain. So that's the important thing. As we are building up the complexity of the model, we are also building, of course, getting more complex results, because there is more CAD data. There is more of geometry included, and that's the challenge. You know, an inverter which works well on a bench has to also be proven that it works well when it's integrated inside the car, and that's really the challenge when we assemble the system. And that's also why we took the steps here to create such a more complex model, because we will not stop at this drivetrain, as I will show you in the following. Just one more slide showing that not only, I mean, we had the AC, we had the frequency domain simulations, but again, we can also take the full time domain simulation, model the whole switching inside this device, where we get the motor currents, and this is the DC current, and we can see that from the time domain simulation we can also identify the three different resonances that I showed you before in the frequency domain simulation. This is nice, it's more advanced, but also it's a little bit more time consuming. That's why in the first slides we took more the frequency domain approach. So now we had the motor, we had the inverter, we put it into powertrain. Now let's put it into the engine bay. So of course, again, now the geometry is becoming more complex, and what we would like to test is a little bit of different shielding strategies. So we have three different cases when there is no shielding, one case where we have a simple shielding around the inverter and the filter, and one when we have fully everything shielded. Of course, that's a little bit unrealistic to have everything shielded, but it's a kind of proof of concept that it's possible to simulate this thing. So that's again the motor, as we have seen already in the powertrain with the inverter here. Then it's put into this powertrain enclosure. Now we include all the surroundings. We include really the bearings and the axles where the wheels are connected, and some holding brackets. And this again will create more and more resonances, because now the geometry is more complex. And here's a comparison of the three cases. So obviously green is the one which is the best shielded, which shows the lowest emission. So this is the conducted emission at this point. So the voltage of the battery calculated here. Then the simple shielded case, and the medium shielded case, and the simple shielded case, which is shown here. And it allows us to also now visualize what is happening there. And again, looking at these resonances at the 37 megahertz, I think this is a value that I already heard from some OEMs, which is typically the resonance connected to the axis itself. And with this simulation, we can basically also see this type of results where the fields begin to, you know, you have a resonance of this length that's typically at 40 megahertz, and you have to find a way to shield or filter it. And last step now, of course, including the full vehicle chassis, the complete high-end now, we have loaded this vehicle chassis and we have pre-meshed it. So we did not fully mesh it into CSD Studio. All the simulations are done with frequency domain solver. Like I said, it's power electronics. So simulations are done with frequency domain solver, and the car itself is too complex to be meshed by CSD Studio. So all the chassis here, and that's why we took another tool from the source system, which is called Power Delta. It's a tool delivered typically by our colleagues from the fluid dynamics, and we have pre-meshed the structure to create such a Nastran model, and then we have loaded this Nastran model into CSD Studio and could assemble everything. So you can see now there was the here's the motor, here are the cables, and then we put all the chassis around it. It's really full detail, and it's possible to simulate even such a complex model, and we can visualize a few things like the currents at 1 kilohertz. basically the operating of the motor. You see how you said you have this rotating field inside the motor. Even in the simplified motor model, you see these things. And then maybe I'll look from the other part and also seeing now, okay, the 1 kilohertz, of course, the field is still pretty much confined to these positions, while at 10 kilohertz, again, you see our axis resonance and so on, all the effects. What's an interesting thing is if we look at higher frequencies, like for example 10 megahertz, you see, of course, I mean, for the EMC emission, it's a lot comes down to how your currents flow. And of course, depending if the car body is connected to the battery, as shown here, or it's floating against the battery, the common mode currents will look different, and also the emitted fields will look different, as we see here, pretty significant, and 10 megahertz, and so on. So this is, I would say, a proof of concept, or it's a model that we have built over the last half year at Dassault System to show what's actually possible with the electromagnetic simulation. We can not only simulate the standalone components like the inverter and just look at the inverter, or maybe just standalone bus bars. We can really integrate all of them into a simulation, including the car chassis, including the engine bay, and so on. Of course, these models, you will not create such a model in a day or in a week. It's a longer process that we have taken here, but that's exactly also my proposal to you. If you start with such a design, use the simulation to accompany your process. As more and more details of your device becoming clear, the more complex you can build up the model. Start with a simple thing, increase the complexity over time, and then going through this process, you will be able to even create such complex models which has been validated over the time. Because you will typically, it will be very, very difficult to build such a model from scratch without testing each of the components itself. So it's always a process creating the simulations model, and again, I'm repeating this very often, but I think it's the most important thing. Start simple and increase the complexity. So you have seen in this presentation the EMC simulation basically at all the different levels. I showed you cables. I showed you the different components like the IGBT module, the filter, and the motor. Then the powertrain, there's a typo, the engine bay, and the full car. It's all that we have been able to simulate using CSD Studio. So which actually brings me to the end, and I'm open for some questions. Thank you.